Okay guys, today we're going to look at where it all started really, and we're going to look at the Big Bang. Now we're going to look really primarily at the evidence for the Big Bang and how that's given us a model for our universe. So let's kick off then, if I can make the tech work, and this is looking increasingly unlikely. We're going to describe the Big Bang Theory. We're going to look at something called redshift and how we use that as evidence for the Big Bang, and we're going to look at other evidence that suggests the Big Bang Theory is correct. But we're going to look at how that model is changing over time as our knowledge increases a little bit. Let's get cracking really. Where does the theory start? Well, it starts with Edwin Hubble. Now, Edwin Hubble was really the father of the model idea of our universe, because he was a student at the sort of early 19th century, and he was sort of an accomplished a sports person as well, but he ended up going to Oxford University to study law, and from that point there he then decided to go to astronomy, and in 1917 he was looking at the Milky Way with the world's most powerful telescope at the time, and he was looking at things called fuzzy nebula. Now you might remember a nebula is a gas cloud. He was looking at fuzzy gas clouds in space, and what he realised was in fact that they were not actually fuzzy gas clouds at all. He actually realised that they were other galaxies. At the time we believed our Milky Way was the universe, and he suddenly realised that actually our galaxy was just one of many galaxies, and the universe was much, much, much bigger than anyone had realised, which is an incredible discovery. And then he made two important observations by looking at them. Observation number one, he noticed, was that the light from these galaxies was shifted towards the red end of the spectrum. The light was redder than it should be. The further away a galaxy was, the more red-shifted its light was. And that was a really crucial discovery and very important in understanding how our universe is expanding. What he concluded from these observations were that galaxies were moving away from our own. The galaxies are moving away from us. The further away a galaxy was, the faster it was moving away from us. And that told him that the universe must be expanding. So that was a massive step forward in our understanding of our universe. So he realised our universe was not just one galaxy, but one of billions of them there, and it's now we're able to put satellites into space and look at the universe with much better telescopes that are off our planet. Makes it much easier to study our universe. One of the first space telescopes that went out there was, of course, Hubble, named after him. So, what is redshift? Why do we know about redshift, and why is that useful? Okay, because why does that help us understand it? Well, when you look at light, we can see that the further away light is, the more that these spectral bands start to appear in the redshift. You can see these bands here and these bands here are identical. However, these are shifted over to the red side of the spectrum and these are shifted towards the blue side. So the further away something is, the more redshifted its light is. So why does that help? Well, that's because of something called the Doppler effect. Now, to explain that, it's arguably better to look at it in terms of sound. So let's think about a car driving along, beeping its horn. Now listen to the sound, the pitch of the sounds that come towards you. Now you can hear the change in pitch of that sound. It gets higher pitched as it comes towards you, it gets lower pitched as it goes further away. Now the sound doesn't change, but your perception does. And that's because the sound waves in front of the car squash together, because the car is moving towards each sound wave. And that raises the pitch, shortens the wavelength. And when it's moving further away, then the sound waves get further apart from each other. And I'll demonstrate that. You can see these sound waves are actually moving in front of the car at exactly the same frequency or same wavelength. As the car speeds up, you can see that they get closer together. and as they move away, they get further apart. So the sound wave changes frequency and wavelength in front of the car and behind the car. If you slow it down again, then you can see that those waves change back. So why does that make a difference? Well, light waves behave the same way as sound waves. As they're moving away from us, those wavelengths are getting longer. So they're shifting towards the red, lower frequency end of our spectrum. That means we can see galaxies moving away from us because the light has changed colour and it's getting towards the red end of the spectrum, not the white end of the spectrum. That shows us the universe is expanding away from where we are. Okay, so this shows you how it changes. You can see these spectral bands shifting further over towards the red end of the spectrum based on how far they are apart. So why do they shift? Well, again, this is gamma radiation, which is what the Big Bang produced. The Big Bang produced huge amounts of gamma radiation, and as galaxies are emitting this gamma and they're moving further away from us, then those wavelengths are getting longer and longer. So instead of being very short wavelength, high energy gamma, they're being stretched to much longer microwave radiation. So the visible stuff is shifting to the longer red end of the spectrum and gamma shifting towards the microwave. So that is a really important bit of evidence that the Big Bang is occurring. What other evidence do we have? Well, in 1964, two scientists by the name of Penzias and Wilson were looking at the Milky Way. They're looking to map signals from the Milky Way. There's a large horn antenna with which to do so. And they kept picking up signals that they shouldn't. These horrible sort of nasty staticky signals. So they first thought, oh, it's because we're near Las Vegas. It must be caused by Las Vegas. So they aimed the antenna directly at Las Vegas and noticed it didn't change. They pointed it away, still didn't change. They then went and discovered there were a load of pigeons up in the nesting in the loft. So they killed all the pigeons, thinking that was causing the background radiation, and it turns out that didn't either. What they had discovered was the cosmic microwave background radiation. What the cosmic background microwave radiation is the leftover noise from the Big Bang, the echo of the Big Bang. So the Big Bang produced lots of gamma radiation. That, as it shifted further apart, has turned into microwaves. And microwaves are coming from all parts of the universe. So this energy is just echoing around the universe. And we can map it, and this is what we have done recently. This is a map of the microwave radiation left over from the Big Bang. If you want to experience this, just tune your radio away from the station and you'll hear that static. That is the leftover noise from the Big Bang. We can hear it if we want to. So what we have now are two bits of evidence that suggest, one, the universe is expanding away, and if it's expanding, it must have started at a single point, a singularity, if we will. And two, it released a lot of energy. How do we know? Because we can still experience that cosmic microwave background radiation. And that led us to a new theory. So what was the initial theory? For a very long time, people just believed the universe was just there. Quite a religious point of view, this. God created the universe, there it is. Based on the red shifting that Hubble had discovered and the universal cosmic background radiation, there was then this understanding, or this idea, theory, that there was a steady state theory, which is the universe is just constantly expanding. And to keep the matter density of the universe sort of constant, new stuff being made in the centre to replace the stuff that's moved away from it. This was quite a popular theory for a long time. And then we came up with the Big Bang theory. Now the Big Bang theory is just a theory, and it's based on the redshift, and it's based on the cosmic microwave background. So what evidence do we have for it? Well, if everything is expanding away, it must have come from a singularity. We have modelled the Big Bang quite effectively. It's a very complicated thing to try to discover because it started as a singularity, this ball of energy that exploded. Energy will turn into matter. There is something called the wave-particle duality, which we just don't have time to go into, so I won't even try. But that energy can turn into matter. Light does it. Photons of light can behave like energy in waves, or they can behave as particles. And matter started to form, tiny subatomic particles, things like quarks. Quarks formed protons and electrons. Electrons and protons started to form atoms. Hydrogen was formed, and then you get fusion into much larger atoms. Later on, as stars start to form. And this expansion of energy turning into matter caused everything to expand and keep on expanding because, as Newton says, anything acting with balanced forces will keep going in a straight line forever. And that's how we believe the universe formed. Questions such as what happened before the Big Bang, we simply don't know. One very glib answer is there is no before the Big Bang, because time didn't start until the Big Bang started. Time is one of the dimensions we perceive the universe in, and that didn't begin until the universe started. So that's one option there. What's going to happen at the end? Well, there's three possible ends of our universe. One is if the mass of the universe is large enough, eventually gravity will slow it down, and then it will start to pull back together again very, very slowly. And that's called a closed universe. What would happen if the mass of the universe is smaller? Well, in that case, if that happens, then the gravity will never be strong enough to stop it expanding, and that will just continually get bigger and bigger and bigger and bigger and bigger forever. That's what we call the open universe model. The third model, the third theory, is that the universe will in fact oscillate. So it will expand, it's a singularity, Big Bang, eventually it will slow down, it will contract again until you get another singularity, and then bang, we'll get another Big Bang, and it will keep going inwards and outwards forever. We have no evidence for this because the universe is only about 15 billion years old, and it's still doing the outward bit. So it may well contract, we just don't know. But those are our current models of the universe. But they're not complete. As a chemist, I quite like the fact that my subject deals with far less uncertainty than physics does, and I do like to take the mick out of my colleagues for that. But what's the shape of the universe? We simply don't know. If we look at a variety of different mathematical models, there's a number of potential universal models that could be, and they're difficult to understand. But we also have problems in the universe doesn't behave the way it should. Our galaxy is not rotating the right way. Thinking about centripetal force and this idea about things orbiting around the centre at certain speeds based on the gravitational force, if gravity worked the way we think it does, then the Milky Way should spin faster in the middle and slower as you get further out. But that doesn't happen. This is what should happen. The speed should slow down as we get further away, a bit like our solar system does. But it doesn't. It orbits at the same speed all the way around, and that's not right. That shouldn't do it. So, why doesn't it do it? Well, what we have to do is come up with another theory. The other theory is that there must be other matter in our universe that enables the galaxy to spin that way. We call it dark matter. Okay, now dark matter is a theory. We call it dark matter because we can't see it. We know the mass must be there because the universe behaves the way it does, but we just cannot see it. How much is that? Well, we actually think that it's about a quarter of the universe. There must also be a huge amount of something called dark energy. And dark energy is this it's a sort of anti-gravity effect that helps power this acceleration that allows redshifts to take place. Now, neither dark matter nor dark energy have currently been proven to exist. Very, very recently, in the last week or so, some evidence for dark matter has been uncovered at CERN. Feel free to have a look at that. But astrophysicists seem to think this is a fairly plausible explanation of how the universe behaves the way it does. But at the moment, that's all it is. It is just a theory. So, hopefully, you can talk about what redshift is. It's a shifting towards the red end of the spectrum. You can describe the Big Bang theory. Singularity, bang, everything starts to expand outwards, releasing huge amounts of energy, which we can see as the universal cosmic microwave background. We can use those observations to come at the theory, talk about redshift providing evidence, explain qualitatively the redshift, you don't need to know numbers, and understand this idea that dark mass and dark matter are things that we don't understand yet. So guys, have a go at the questions please. Any questions, comments, queries or concerns, you know where to find me. Otherwise, take care of yourselves and I'll see yourselves soon.